Welcome to AI Frontiers. Today, July 14, 2025, we're exploring 17 groundbreaking machine learning papers that showcase the field's evolution from raw computational power to intelligent, efficient systems. These research breakthroughs span efficiency optimization, privacy-preserving learning, and theoretical foundations that are building tomorrow's trustworthy AI systems. From memorization isolation techniques to real-time 3D generation capabilities, today's discoveries represent the cutting edge of artificial intelligence research. Picture this: somewhere in a research lab right now, a computer is learning to understand human emotions just by looking at pictures, while another machine is discovering new drug compounds by reading scientific papers like a human researcher would. Meanwhile, a third system is predicting energy demand for an entire city by analyzing patterns invisible to the human eye. This isn't science fiction, this is the reality of machine learning research happening today. Researchers have achieved a remarkable 278-fold speedup in time series analysis, while others have made real-time 3D content generation possible for the first time. These aren't just academic exercises, they're the building blocks of systems that will diagnose diseases, optimize energy grids, and help us understand the fundamental nature of intelligence itself. What makes today's research particularly fascinating is how it collectively tells a story about where machine learning is heading. The field is witnessing a fundamental transition, moving beyond the bigger is better mentality toward smarter, more efficient, and more interpretable systems. These researchers aren't just scaling up existing models, they're fundamentally reimagining how machines learn, adapt, and solve problems. This shift represents a maturation of the field, where brute force approaches are giving way to elegant, principled solutions that can operate effectively in real-world conditions. The focus has evolved from simply achieving high performance to building systems that are efficient, interpretable, and responsible, systems that can be trusted with critical applications from healthcare to autonomous vehicles. To understand the landscape of machine learning research, imagine it as a vast ecosystem, like the Amazon rainforest, but instead of trees and animals, we have algorithms and data structures. Just as the rainforest has different layers, machine learning has its own complexity layers. At the canopy level, we have high-visibility breakthroughs that make headlines, large language models that can write poetry, computer vision systems that can diagnose cancer, and robots that can navigate complex environments. But the real magic happens in the understory and forest floor, the fundamental research that creates conditions for those canopy breakthroughs. This includes optimization algorithms that make training faster, theoretical insights that explain why certain approaches work, and methodological innovations that make AI systems more reliable and interpretable. The field of computer science machine learning sits at the intersection of mathematics, computer science, and cognitive science, asking fundamental questions about how we can create systems that learn from experience while remaining reliable and safe. The first dominant theme reshaping the field is efficiency and scalability optimization. Think of this as the field's equivalent of learning to do more with less, like a master chef who can create a 5-course meal with just a few ingredients. Researchers are discovering that bigger isn't always better, and that clever algorithmic design can often outperform brute force approaches. One breakthrough demonstrates how parallel processing can speed up complex 3D rotation calculations by nearly 5 times without losing any accuracy. Another shows how sparse attention mechanisms can reduce computational complexity from quadratic to linear scaling, making previously impossible large-scale problems suddenly tractable. Perhaps most impressively, researchers have achieved a 32-fold reduction in model parameters while maintaining performance, proving that sophisticated AI can be made accessible on devices with limited computational resources. These advances represent a fundamental shift in how we think about AI deployment, from requiring massive data centers to running efficiently on everyday devices. The second theme focuses on robustness and adaptability, essentially, creating AI systems that can handle the messiness of the real world. Imagine trying to teach someone to drive, but they've only ever practiced in perfect weather on empty roads. When they encounter rain, traffic, or construction, they struggle. Similarly, many AI systems perform brilliantly in controlled laboratory conditions but falter when deployed in the wild. Researchers are developing techniques like continual learning, where systems can acquire new knowledge without forgetting what they've already learned, and federated learning approaches that can handle intermittent connectivity and varying data quality. These advances are crucial for deploying AI systems in real-world environments where conditions are unpredictable and data quality varies. The goal is to build systems that can adapt and continue learning throughout their operational lifetime, much like how humans continue to learn and adapt to new situations throughout their lives. Privacy-preserving learning represents the third critical theme, becoming increasingly important as AI systems handle more sensitive data. Picture a group of doctors who want to collaborate on a research project but can't share patient data due to privacy regulations. Privacy-preserving machine learning techniques allow them to train models collaboratively while keeping individual patient information completely secure. The research includes entropy-based adversarial training that can sanitize sensitive information from learned representations while maintaining the model's predictive power. Remarkably, synthetic data generation techniques have achieved performance improvements of up to 871% compared to using original datasets. This finding has profound implications for privacy-preserving machine learning, where synthetic data could enable sophisticated analysis while protecting sensitive information. These techniques are like creating secure shipping containers that protect sensitive cargo while allowing beneficial trade to continue, enabling AI deployment in sensitive applications from healthcare to finance. Today's research has yielded 6 game-changing discoveries that could reshape how we build and deploy AI systems. First, researchers achieved a 5 times speedup in parallel diffusion model sampling for 3D rotations, enabling real-time generation of 3D content for virtual reality and robotics applications. Second, scientists discovered that neural networks can undergo phase transitions, literally switching from pattern matching to true algorithmic thinking when learning streaming parity tasks. Third, the development of memorization sinks allows isolation of memorized content from general language abilities during training, addressing critical privacy and copyright concerns. Fourth, new techniques using random Fourier features achieved a 278-fold acceleration in time series segmentation while maintaining comparable accuracy. Fifth, carefully designed synthetic datasets outperformed original data by up to 871% in some applications. Finally, model compression research achieved a 32-fold reduction in parameters while maintaining performance, making sophisticated AI accessible on resource-constrained devices. These breakthroughs collectively represent a new era of efficient, controllable, and deployable AI systems. For our paper of the day, we examine memorization sinks, isolating memorization during large language model training by Gaurav Kasal and colleagues, which addresses one of the most critical challenges facing large language model deployment today. The problem is significant. Large language models trained on massive internet datasets sometimes memorize specific passages verbatim, creating serious privacy and copyright concerns. Imagine if a model trained on medical records could recite patient information, or if a model trained on copyrighted books could reproduce entire chapters. This memorization problem has been a significant barrier to deploying these models in sensitive applications. Previous attempts focused on post hoc removal, training the model first, then trying to remove memorized content afterward. But this approach showed limited success because memorization becomes mechanistically entangled with general language abilities. It's like trying to remove specific memories from a human brain without affecting their ability to speak or understand language. The memories are so intertwined with general capabilities that removing them damages the whole system. Kasal and his team took a completely different approach with their MemSyncs framework. Instead of trying to fix memorization after it happens, they designed a system that prevents problematic memorization from occurring in the first place. The key innovation is a sequence identifier mechanism that activates a unique set of neurons for each repeated sequence, creating dedicated neural circuits for memorized content that are separate from those responsible for general language understanding. Think of it like this: imagine your brain had separate filing cabinets for different types of information. One cabinet stores your general knowledge about language, grammar, and communication skills. Another cabinet stores specific quotes, phone numbers, or addresses you've memorized. If you needed to forget a specific phone number, you could remove it from the second cabinet without affecting your general language abilities stored in the first cabinet. The researchers validated their approach by training models at the billion-parameter scale, a massive computational undertaking that demonstrates the practical feasibility of their method. This represents the first proof of concept demonstration that simultaneous generalization and memorization isolation is achievable in practice. The impact of MemSyncs extends far beyond solving the memorization problem. The framework provides a general approach for building controllable neural networks where specific types of content can be isolated and managed independently. This has applications in bias mitigation, content filtering, and model editing, anywhere we need to selectively modify model behavior without global degradation. The research also contributes to theoretical understanding of how neural networks store and retrieve information, suggesting that neural networks can learn to create specialized storage mechanisms for different types of content, similar to how biological brains may have specialized regions for different cognitive functions. From a practical standpoint, this work could enable deployment of large language models in sensitive applications where memorization has been a blocking concern. Medical institutions could use these models to assist with diagnosis and treatment recommendations without worrying about patient privacy. Publishing companies could allow AI systems to analyze their content without fear of copyright infringement. Educational institutions could deploy AI tutors that can engage with copyrighted materials while respecting intellectual property rights. Looking toward the future, today's research paints a picture of a field that's maturing rapidly while maintaining its innovative edge. Think of machine learning research as a river system. What we're seeing is the convergence of multiple tributaries into a powerful main current carrying us toward truly intelligent systems. The efficiency and scalability work is like improving the river's flow dynamics, making it possible to transport more information with less energy. The robustness and adaptability research is like building better navigation systems that can handle changing conditions and unexpected obstacles. The privacy-preserving techniques are like developing secure shipping containers that protect sensitive cargo while allowing beneficial trade to continue. Domain-specific applications represent the river reaching different communities, adapting to local needs while maintaining its essential character. The theoretical foundations work is like mapping the river's source and understanding the geological forces that shape its course. Benchmarking and evaluation efforts are like establishing lighthouses and navigation aids that help everyone travel safely and efficiently. Where is this river taking us? The research points toward a future where AI systems are not just more powerful, but more trustworthy, efficient, and aligned with human values. The work on memorization isolation shows we can build systems that are both capable and controllable. The efficiency breakthroughs suggest we can democratize access to sophisticated AI by making it run on everyday devices. The robustness research indicates we can deploy these systems in critical applications with confidence. Perhaps most exciting is the theoretical progress helping us understand why these systems work and how to make them better. We're moving from an era of empirical AI development, trying things and seeing what works, to an era of principled AI design based on solid theoretical foundations. This shift promises to accelerate progress while making it more predictable and reliable. The convergence of these research directions suggests we're approaching a new phase where unified frameworks combine multiple approaches, like the MEMSyncs work that provides a general architecture for controllable learning. Today's research represents seeds planted in fertile soil, and their impact will grow and multiply in the months and years ahead. This analysis was synthesized using advanced AI systems to process and interpret the latest machine learning research from the archive preprint server. The text-to-speech synthesis is powered by Amazon services, while image generation utilizes Google's tools. All content underwent human expert review to ensure accuracy and clarity, though some oversights may exist in this rapidly evolving field. The goal is to make cutting-edge AI research accessible to a broader audience while maintaining technical accuracy. References to original papers are provided for those who wish to explore the research in greater depth. This process represents the collaborative potential of human expertise and AI capabilities working together to advance scientific communication and understanding. As we wrap up today's exploration of machine learning frontiers, we've witnessed incredible diversity and sophistication in current research. From parallel diffusion models generating 3D content in real time, to neural networks learning true algorithms from finite data, to systems isolating memorization while preserving general capabilities, each advance represents a piece of the artificial intelligence puzzle. What's particularly encouraging is seeing researchers focus not just on making systems more powerful, but on making them more responsible, interpretable, and beneficial to society. The work on privacy-preserving learning, emphasis on efficiency and accessibility, and attention to theoretical understanding all point to a field maturing in the best possible way. These aren't just academic exercises, they're building blocks for AI systems that will help doctors diagnose diseases, scientists discover new materials, engineers design efficient energy systems, and educators create personalized learning experiences. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, We simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by Archive Preprint Server.